Hello, welcome back. This is Calculus by Dr. Oz. Today, we're going to choose a basic integration formula from the list of formulas that we had in the lecture notes. And I want to remind you what those formulas are first. Let me just show what they are. There we go. So these are all integration formulas. You have 20 of them. Please practice those before you hit the road. Also, we have some integration techniques that we are going to use along the way. Let me show also what they are. So this is, you can take this as like guidelines to fit the given integrand to the one that you can use the basic integration rules for in the previous slide. So these are mostly like algebraic and trig techniques. And one technique, as you see at the top, is expanding the numerator or expanding quantity powers in general. The other one is like separating the numerator. So you may have like a full fraction, rational function provided to you. So you can actually split that fraction into smaller fractions. And completing the square is one of the most well-known techniques, and I'm going to use this time to time in the series of videos for this section. So make sure you have a good grip of that. And dividing the improper rational functions is another technique. So improper means like the degree of the top of the polynomial in a rational function is greater than or equal to the degree of the bottom. So that requires a polynomial division. Okay, so make sure you have also a good grip of polynomial division. Adding and subtracting is another technique to simplify the given rational functions. And we have the trig identities, Pythagorean identities, three kinds, one for sine and cosine, tan and secant, and a combo of those. So you have three of them in total. You will see in some of the videos that I'm going to use them simultaneously. And obviously multiply and divide by the conjugate of the given function, especially when you have a rational function. And if the bottom is like sum or difference of two terms, you can actually multiply top and the bottom by its conjugate. So conjugate means like things come with opposite sign. So if you have difference, then it turns out to be sum. If it's sum, then it turns out to be a difference. Okay, so make sure you have a good understanding of these techniques here, and because time to time, as I told you, not in just this section, but in this chapter, I'm gonna rely on to these techniques time to time. All right, so let's start. All right, let's start with part A. We have negative 2x divided by radical x squared minus 4. We have the formulas listed right here. So we're going to pick the most relevant formula for our case. Okay, since we have like x squared minus 4 in the bottom and negative 2x at the top, I think u substitution is going to work fine. And then we should probably use u to do n du formula here, which is number 4 here. Okay, number 4 seems to be like very reasonable for part A. Okay, so what I'm going to do here is that I'm going to take u to be the bottom without the square root. Okay, and then I'm going to look at du. So du is going to be 2x dx. Okay, that's good because now I can replace x dx by 1/2. Okay, so this is part A. And then here we go. I have negative 1/2. I can pull the negative sign out to go with 1/2. Du over radical u. And that is the same as u to the power of negative 1/2 du. Okay, because we can use the reciprocal idea. We can get to the negative exponent. So this way, now we have the form number 4 in the list, right, we converted the integral to the integral of u to the power of n. So now I'm going to use this formula, u to the n plus 1 divided by m plus 1 here. So all I'm going to do is to add 1/2 to the exponent and divide, so adding 1 to the exponent and divide by the new exponent. Okay? Let me just continue on the left here, that this turns out to be u to the 1/2 divided by 1/2, and you have another negative 1/2 here, plus c. So this 1/2 here is going to cancel this 1/2. Turns out that this becomes negative radical u, because u to the 1/2 is radical u. And then we have to go back to the original variable, which was x. So before the u substitution, right? So that's plus c. Okay? I think that takes care of part A. All right, for part B, we have secant x, tangent x, and going back to the basic integration rules here, I can see number 16 here, which comes with secant u, tangent u, du equals secant u plus c. So in our case, u equals x. So in fact, for this part B, we don't need a separate u substitution. So we have secant x, tangent x dx, and in the formula it is integrated as secant x plus c. There you go. So I'm going to write it as secant x tan x dx is secant x plus c. So again, that doesn't require any kind of like u substitution. As you see, we can simply use the formula number 16 here for u equals x. And all of the formulas that you see here comes with u. So if u is x, so you can get the x relevant formulation of that. If u is not equal to x, then in the original integral, you have to have a u substitution so that you can put your integral in one of those forms. All right, in part C, we have 1 over x, radical x squared minus 4. So let's go ahead and check which formula is more applicable. So number 1 through 10, they don't look to be similar. Well, number 20, as you see on the right, is very similar. It's du over u, radical u squared minus x squared, is 1 over a arc secant, absolute value of u over a plus c. So we should check if ours is like u squared minus x squared type stuff. So for u equals x, essentially, so for u equals x, number 20 is in fact what we have here, right? So so therefore, going back to the formula, I'm going to grab a, and then what is a in our case? Well, this is like x squared minus a squared. So essentially, this should tell us that a equals 2. Okay. There we go. A equals 2, and then now I have dx x squared minus 2 squared. So I have 1 over a arc secant u over a. Okay. So 1 over 2, 1 over 2 arc secant u over 2, which is x over 2, the absolute value, by the way, plus c. Okay. I think that takes care of that. And this way, we are done with all 3 integrals. And again, make sure that you have like a good grip of the basic integration rules, because this is our basis. So for the rest of the chapter, like chapter 8, so we're gonna always refer back to the basic integration rules, and one way or another, we're gonna put the given integrations into one of those forms by a U substitution or integration by parts, or any type of transformation that we're going to see in this chapter. All right, that is the end of it. Thanks for watching. I'll see you in another video. Bye.